Welcome back. In last lecture, I just touched the SN1 and E1 chemical reactions, and in this lecture, I'm going to try to go more in depth and show you the details of the mechanism. And in this case, we have bromide that attached to carbon, and our carbon is a tertiary carbon, and the solvent is methanol. So this is going to be our solvent. In the presence of such a solvent, there is a high chance that bromide will leave the system, and we will get carbocation. So the first step of the reaction, it will be formation of the carbocation. So this is our substrate, and there is a bromide here, and this one, it will give you an equilibrium, and you will get an intermediate, and the intermediate, it has a positive charge. Okay, so this is a tertiary carbocation, and of course we do have the bromide. This bromide, it will be the leaving group, and so I go -1. And now this step, it will be slow. So this is going to be the rate determining step. And when you do calculation and you try to figure rate of the reaction, you're going to read this rate. And so the EA for this step is going to be the highest one. Now, what will happen with the intermediate? There are two possibilities that can happen to the intermediate first step. And the first step is going to be this. We have a carbocation, and this carbocation, it will react with the solvent. Okay, our solvent is methanol. It has oxygen with 2 lone pairs. The oxygen with lone pair, it can be added to the carbocation, and from any direction. Why from any direction? Because in reality, this carbocation is a p orbital that's pointing up and down. So I can reach it either from the top or bottom, and I don't see any difference here or any preference for any side. And if that one happened, we get such a product. So let's say we attached oxygen here. Now oxygen, it has a positive charge. Still, it has 1 lone pair, and okay, there is a methyl group there. Okay, and again, this step is going to be really fast. So we will have activation energy for it, but E2 is going to be smaller than E1. And the third step, intermediate, in the presence of solvent, it will lose hydrogen. Okay, we do have solvent inside the. We do have other solvent. Sorry, we have other methanol molecules inside the solution. So one methanol molecule can get involved and take hydrogen. This hydrogen, the one I'm going to highlight it, take this one out of the system, and if this one happen, we're going to get such a molecule. So we will get this, and now we have O here attached to methyl. This oxygen, it has 2 lone pairs. Now it has a 0 charge. Plus, okay, we're going to get methanol, okay, attached to oxygen. Sorry, methyl group that attached to oxygen. And oxygen, it has 2 hydrogens. So now this one, it has a positive charge. Okay, so the final product will be this. I'm going to highlight the final product. This is going to be our final product. We got nucleophilic substitution. We replace technically the bromide with a methoxide group. So let's write the product. So the first product will be this. We started from here. We had bromide, and we treat it with alcohol. This group replaced the bromide. The bromide got kicked, and now we got this molecule. Okay, so this is going to be a nucleophilic substitution, and clearly I replace the bromide by a methoxide group, and this I'm going to highlight it. So I'm going to say rate of the reaction. Rate of the reaction is going to be equal to K multiply. Only thing that's I do care about it here, or affected rate of the reaction, and is going to be concentration of the starting compound. Why? Because that step is the slowest step. And so I'm going to say rate of the concentration of the substrate, and the molecularity is equal to 1. So I'm going to say this one is to the first, and this is going to be SN1 is a substitution nucleophilic, and because we have one for the molecularity, one substrate, one molecule was involved, we call it SN1. Okay, let's draw the graph. Okay, so let's say we started from somewhere here, and we got the product somewhere there. Okay, first step, okay, we went through it. Okay, barrier, we got an intermediate. Okay, and then that intermediate went through a small barrier, got you in something. So let's see, we got this one was the this one was the first intermediate, and that's the second intermediate, and then the product. Okay, so one intermediate, that's first intermediate, and here I got the second intermediate, and now I go through a small barrier and get the product. Okay, so my reaction in this case is running it through 3 steps, and the biggest activation energy, I can see it between the reactant and the first transition state. This one, it will be the biggest activation energy, EA1. This is going to be EA2. And this one, it will be EA3. EA1 is bigger than the second, bigger than the third one. So I call this one, so forgive me. I call the first step the rate determining step because it's the biggest one. And here we have a reactant and we got a product. Okay, what should I call the top points? Transition state 1. This is going to be transition state 2. And this is a transition state 3. So I have 3 transition states because I had 2 intermediates. Okay. The second thing that can happen to the carbocation, so let's say after the first step, okay, when this one happened, and we got the carbocation. So let's say we are here, and the first step happened. We got the first hour intermediate is a rate determining step. The second step, okay, we have, let's say, a base, and that base goes after hydrogen abstraction. So it will take hydrogen from the system, and we will have elimination product. So I do have hydrogen here, or hydrogen there, and hydrogen also there. On those hydrogens, because our neighbor to a carbon with a positive charge, now their acidity is going to go up. So I'm going to say the acidity will go up. Again, why it will go up? Because this carbon, now it has sp2 hybridization, and electronegativity of sp2 is really high. If you have a group attached to your neighbor, okay? So we have a carbocation attached to a carbon that it has hydrogen, and the carbocation, because it has higher electronegativity, is going to try to steal electron from it. So it will try to steal electron in this direction, okay? Again, we will have loss of electron from neighbor methyl to the carbocation. So any of those hydrogen, very soon they will be acidic. And if that one happen, then we have this possibility. Those H, they can react with a solvent, or let's say a base. Okay. Say, I'm going to say a base here. Okay. And the base, it will take those hydrogen from the system. Again, your solvent can behave as a base and take the hydrogen out of the system. And so what do I get? If that one happen, now base will attack that hydrogen, and hydrogen will give those 2 electrons and to carbon, and carbon now it will share them with carbocation. So now I have a double bond. I got a double bond, and now what happened with the hydrogen? Hydrogen will be taken by the base. Now the base is going to have a positive charge. Okay, again, I got a solvent with a positive charge. Why? Because it has hydrogen. And is it possible to get, for example, this? Yes, this one can happen. Your solvent can take technically the methyl. The hydrogen out of the system. But the product, it will be alkene. This is the main product. And this mechanism, we call it elimination. Okay. Why elimination? Because we took hydrogen and bromide out of the system and we got alkene product. And because it's elimination, I'm going to say this is elimination. I will show it by E. And again, because the molecularity is 1, I'm going to call it E1. And the rate for it, rate of the reaction, is going to be equal to K multiply concentration of the substrate or the alkyl halide to the first. Okay. This mechanism is going only through 2 steps. Okay, through only 2 steps and the 2 steps. So I'm going to say okay, let me draw it for you. So first step of the mechanism, we said we're going to create, for example, an intermediate, a carbocation. Now that we have the carbocation, that carbocation is going to go through for loss of hydrogen, and it will give you the product. And this, for example, this is the barrier for it for the second step. Barrier for the second step versus barrier of the first step is nothing. So activation energy here is way higher than the second step. So I'm going to say EA1 is bigger than EA2. That means the first step, it will be the rate determining step. And the only thing you had was the reactant involved in it. So if you look at the transition state, your transition state, it has only 1 molecule in it. So you say rate of the reaction is going to be equal to K multiplied, because you had only 1 molecule and that molecule was your substrate. You will say the molecularity is going to be to the first. And after that one, what do I get here? I will get this product, and this product is alkene. Okay, if I want to show if I want to show level of the substitution product, the substitution product will be somewhere here, and so that's going to be product of SN1. Why? Because they will be saturated, and the unsaturated compound is going to be unstable, less stable than saturated compound, and so that's the reason I'm showing it a higher level. And this product is going to be this one, so it will be OCH3, okay, for SN1. Okay, I'm going to stop the lecture here, and thank you very much.